Record on this computer. Totally forgot to record stuff this morning for my other class, but that's okay. All right. So as I mentioned on Tuesday's class, I was unable to really respond to any emails that may have come in, so I'll try to respond to those. I'm going to be spending the weekend essentially doing grading, working on my yard, and basically meeting with students. Those are essentially my 3 tasks for the weekend. So if you need to meet with me, please, send me an email and I'll try to arrange a time. Right? If you still need to find the time to take your exam because you were sick or something, there were a number of people who tested positive for COVID, and missed the exam because of that. Not like a huge number, but it was a number that was not 0. So again, if you're in that kind of situation, just simply email your TA, right? Just email your TA and you'll be able to and find a time with them to take it. Okay. So as far as the exam, I know a lot of you are concerned about your grades because you might be concerned about how well you did. I do understand that a couple of the questions I asked, like one of the questions I asked was with drawing stuff was a bit more geometry based than you may have liked. I did make a rubric for that question, so don't worry. You're probably going to get some amount of partial credit for that one. Worst case scenario for like this exam, right? I'm planning 3 exams, each worth 10% of the grade. Worst case scenario, I can just drop the percentage that this is worth, right? Make this one worth less than 10%, bump up the percentage of the others, right? So that's all going to depend on student performance here and what our overall grade is. Because I'm grading these things, I'm seeing plenty of answers that need improvement. I'm seeing plenty of answers that are correct, right? I'm not seeing like anything decisive, like, oh, this is something that the second to last problem almost everybody got. That's like about the second to last problem almost everybody got. The A and B manipulation problem, a surprising number of people got that one. I thought that one was going to be a lot harder. Again, I'm talking about this abstractly because we've got students who haven't taken the exam yet. So that will do that. Now, a lot of the second exam will rely off of so topics you can expect on the second exam is file reading and and that kind of stuff, as well as string manipulation. Like, so a lot of what you're going to be doing on your on homework 7, the hurricane tracker, you can expect similar stuff minus the turtles, right? So for example, a question I asked in the previous exam for the second exam was, here's a file suppose you have a file that has like, 1 number per line that has the average temperatures for Philadelphia in them each day, right? Give me the average temperature for the average temperature, so basically reading everything in the file, adding it all up, giving me the average, right? So that's not terrible because you can kind of sort of start to figure how to piece that together. Monday, so next Tuesday and Thursday's labs will be talking about doing more stuff with file reading. We'll be as well as starting our talk about Monte Carlo approximations, which sounds a lot more difficult than they are, but it's just a fancy way of for us to say we're being lazy so we don't have to do math. So for today, I figured though, I don't have it linked anywhere on Google, but I figure we can open up Runestone and we can tackle one of the ones I haven't really done before in class. Because normally I just show how to write a file. It's actually not that exciting to show how to write a file. Writing a file is fairly straightforward. I can show it at another time. Pretty sure I go over it, but all you have to do is you open the file in write mode, and then rather than reading from it, you just type write and write the string you want to. That's it. It makes it easy. C is a pain. C makes it a real pain. C++ is also a pain. Java's not too bad. Because with Java, they teach you how to use Scanner, and you can use Scanner to read files. So that's not too bad. So I figure let's go ahead and try doing, let's see. So let's see, we've done, let's see, did we do substitution cipher at all? So we can do either, we can talk about one of two topics. We haven't done this project yet, right? Substitution cipher? Nope. So we could do either, we can either do cryptography or image processing. Image processing, okay. Image processing is pretty fun. We don't know, I don't, so okay. One of the wonderful things about Runestone is that things are kind of baked in, is that things like files and file reading are baked in, right? So you don't have to worry about opening files on your computer and downloading it. It's part of the reason I like Runestone so much. So images are huge, are pretty big. They're, in these days. You know, there's an entire TV show, Silicon Valley, that's predicated on basically how do you make images, you know, storing images and videos more efficient as kind of the plot device for it, basically making it more efficient to compress those and store those. So the idea here is that we've got this image, the Golden Gate Bridge, which is entitled golden underscore gate.png. All right. And it's uploaded to this file, to our thing, and there are just things we can do with it. So let's take a look at this code we have already. I'm going to go ahead and comment out. I'm going to comment out basically all the code in here right now. Okay, because it's saying, oh, hopefully you've read the stuff about image processing, and I certainly haven't. I don't need to, but let's talk about it for a second. Okay, images are on your computer are these square on your computer. Images are squares, essentially. Remember what I've been talking about with pixels, that everything on you can't really draw perfect circles because everything on your computer is just made of a bunch of squares, picture elements. So we operate on, so as a result of programming, computers operate in a different coordinate plane than your typical XY plane, right? The typical XY plane is replaced with row column format, right? So the rows tell you which way you're going to go up and down, and your columns tell you how you're going to go across, which is and we talk about it in row and column, which is kind of the reverse of X and Y. It's a bit weird. To further confuse matters, well, this is less confusing, right? You've got a coordinate plane, right? And you've just got different quadrants of your coordinate plane, right? Typically, you work here when you're working in like 2D space, and you don't care about negatives. In computer science, for weird esoteric reasons that seem very arbitrary to me, but actually make sense if you think about how arrays are represented and 2D lists are represented, we work in this coordinate plane over here. The one that goes 0, -1, -2, -3 in the y-axis, and then works the standard way we would think it would work in the x-axis. So as you can see, for this picture, basically the coordinate plane, it starts 0, 0 over here, and the horizontal direction is from 0 to whatever the width of the image is, and then 0 going down is the way the height works. This is true if you're for whatever kind of format we're using for computers. Turtles are the exception because they are explicitly working on a color plane. Okay. So over here, again, every image you see is made up of pixels, individual picture elements. So each square has, and the way a picture is that basically we've got a format that says this point at 0, 0 is this color. This point at 0, 1 is this color. This point at 0, 2 is this color, and so on and so forth. That's how it draws it. And your computer is very efficient at drawing this. And sometimes we need to be a bit more efficient than your computer can be to really draw things that change very rapidly, very quickly. and maybe do some math calculations to figure out how things are drawn. And so we have to get these nice expensive things called graphics cards. And in order to, play video games that require these kind of calculations to be done very, very fast. Okay. So again, all it is just basically a coordinate plane, and we've got, and the points are colors. So what color model do we use? Color is annoying because if you ask any kindergartner like my kid how color works, they'll say, oh, if you mix, if you mix yellow and blue, you're gonna get green. And the primary colors are red, yellow, and what is it? Green, blue? Yeah, the reason I'm hesitating is because that's not how it works here. Because that applies for mixing paints. We're not mixing paints in this class, we're mixing light. And that works completely differently. Because the more light you add, the closer you get to white. The more paint you add, the more closer you get to black. Works completely differently. Your computers, right? Each pixel on your computer is made up of subpixels, which you don't have to worry about because you don't program those individually. Okay. I'm just kind of talking about this just so you understand how these things work. I'm not talking about the Pixel phone. I'm talking about Pixel. No. Right. Right. So, notice over here that like with this picture, we've got individual pixels. Each individual square is just an individual color. Right. So let's see. So what we see here are basically examples of subpixels, where you have little red, green, and blue lights that are next to each other. And what your computer does is that according to whatever it's supposed to draw, it changes the intensity of that light, of each of those lights, to make a certain color. Okay, and you have to be very zoomed in to see this because, again, your pixels are already small, and these are even smaller. Okay. But regardless, you have red, green, and blue. And the way it works is that each color has an intensity that varies from 0 to 255. Why 255? Because most color is in an 8-bit format, meaning that in other words, there's 8 binary digits, 8 zeros and 1 dedicated to telling you how strong it is, right? Okay. And the idea here is that if you want the image to have a lot of red light in it, you say there's 255 red in it. And if you say that you don't want any red in it, you just tell the red amount to be 0. If you set all the colors to be 0, all 3 of the colors, red, green, and blue, to be 0, you're going to get black. You set all of them to 255, you're going to get white. Okay. Now, as they point out, since you have 3 basic colors and each of them have 256 different positions, 0 up to and including 255, you have 256 to the third possible color or combinations. That's a lot. Occasionally, we've got stuff like 10-bit color that's now starting to be there, but honestly, again, it's worked pretty. 8-bit color has worked pretty well for us right now. But so if you want red, you set your red to be 255 and your blue and green to be nothing. Green to be 255 if you want green, and blue to be this if you want 255. If you want yellow, and this is a bit weird, you put up the red and the green all the way and keep the blue down. Because light works differently. Color is complicated, especially, right? Right. There are, for instance, the color is 3 primary colors mixed together, or a rainbow, and each color is a wavelength. And then they talk about 3-ish primary colors mixed together, depending on your color model. Red, green, blue, red, yellow, blue, cyan, magenta, yellow, and black, right? For printers, right? Abstract multiple dimensional gamut, right? Because also, by the way, What you see on your computer may be different than what you see on somebody else's computer because of differences in the way computers are built. So at the end of the day, hopefully somebody else's problem is just, you just have to be aware that color light wiki, that it works differently. Right? It works very differently depending on whether you're working with light or paint. Additive coloring, where you add color together, right? Subtractive color combining yellow and magenta yields red, right? Using dyes, pigments, inks to absorb some wavelengths of light and not others. Here we're adding wavelengths of light. That's what the difference is between color models. Like I said, it's annoyingly complicated. So just keep in mind that it works a bit differently than you might think it does. So the image class so we're going to be working with the image library. It has two things that we care about, two objects that it creates. An image, a big picture, and a pixel, one tiny little piece, a square of that. Okay. And we can, each pixel, we can create a pixel by specifying, hey, here's a pixel and I want it to have these colors. And then for each individual pixel, you can get the amount of red, get the amount of blue, or get the amount of green in it, or change it. Okay. Using get color and set color. So here, this is some code, for instance, that creates a pixel with 45 red, 67 green, and 200 blue. And it changes and then we change, this code would change the red to being 66 as opposed to being 45. And here, this would make the blue and the green identical amounts. All right. So back to here, image processing. One of the most common things that we do with pictures these days are filters of some kind. There's many different kinds of things. Some of them are just simply to make things look nicer. Other kinds of filters are to do some kind of reconstruction, which is what we get to later in this one and why I got interested in this one. So there's a few here. The first thing we typically like to try is something called grayscale. It's not black and white, which is black and white is like literally either a pixel is black or it's white, meaning all the colors on or all the colors off. And it's very kind of hard to just see them. It's not many pictures translate well, but grayscale, which is what old-timey TV looks like, that's easier to do. Basically, you get grayscale by setting all of the colors equal to each other. So all the colors being either 0 or all the colors being 128, and that gets you a nice decent gray. And then like if you set them all to 200, that's like a nice dark gray. So when they're all equal, they're gray. So let's look at this code. So we import the image library, and what this does is that this creates an image. It gets the height and the width of the image. What it says is the image window. And then it draws that window. Okay. And then there we go. New pixels not defined. That's fine. Okay, let's comment it out. So this is what our picture is in this window. We draw it, then we delay it, and then we draw it again. And so what it does is that we are able to draw these pictures in the browser. So over here, what we have is a nested for loop that goes over this image. It says for every row in the height, right? Rows are from top to bottom. And then for every column in it. So every pixel going across. So for every row, let's look at each pixel in that row. Okay. And what we do is that we get the pixel over here. Now I can change this image to being like completely red by saying, hey, let's see, new pixel is equal to, let's create a new pixel. And let's set the red to be 255 and the green to be 0 and the blue to be 0. Right? And then if I do uncomment this image.setPixel at the row, column and row I'm currently at. Interesting that it does column and row there. Oh, because it's X and Y. Yes. I can, and then I tell it to draw, it slowly draws every single pixel to be red. What I'm doing is I'm replacing it. Instead, what we want to do here is change everything to be grayscale. So how do we do that? Well, that would just make everything the same color of gray, but we want to make it grayscale where basically every pixel is its own shade of gray. Yes. Yep. You would. So what we do to make it gray is that we grab our pixel, we take the average of those 3 colors. Okay. Average of the red. So you take the red, green, and blue, add together, and then divide by 3. Congratulations, we now have the gray value for this pixel. Then we just create a new pixel with that amount and set that up. So going all the way back here to 1. Oh, yeah, it's still drawing, so I can't cancel it because stuff. Here, if you change this though to 1 to 2000, apparently this will speed it up a lot. That's good to know. Okay. So if we run this now, ooh, wow, that did speed it up a lot. Okay, so now what we want to do, we go back to our original, is that we want to fill in the blanks. We want to calculate our gray value and then make each of these the gray value, because all of them have, for red, green, and blue, for it to be grayscale, we want them all to be identical. Make sense? All right, so why don't you take a couple minutes to try that out, right? This is one of those cases where it looks complicated, but you're just applying what you already know. Remember, what we're doing is that we're taking the average of these. How do we get those values? We get them by using, so we have a pixel, right? And we can use p.getRed to get the amount of red, p.getBlue to get the amount of blue, p.getGreen to get the amount of green. Yes. Well, what you want to do is use that to calculate the gray value. We want to calculate the gray value by adding together the color intensities and then taking the average of it, dividing by 3. Yep, it's one of those, oh, it's that simple? You add everything together and divide by 3? It's exactly what we're doing. Remember to see if you've got 4 blanks to fill in. You've got gray value, red value, gray value, new red, new green, new blue. I'm going to give it another minute because I want to keep moving forward with this, and then I'll always show you all how to do this. Mm-hmm. All right. So all we're going to do here is that we're going to figure out what the gray value should be, is that we're going to take the pixel over here, get its red value, get its blue value, and then get its green value. And then we have to remember order of operations before we divide by 3, because if we divided by 3, it would divide green first, and then we'd add in the other things, which would not necessarily be. When in doubt, just always use parentheses, to be honest, because I can't be bothered to think about order of operations. So I just use parentheses all the time to say what I want. So also, I probably want these to be integers. So I'll just divide by 3 like that. And then all I have to do for the new red, the new green, and the new blue is put in gray value for each of them. Because what we do is we make them all equal. So here, and now we can see it that we're slowly like all the colors being drained, like one of those episodes from TV or something. While we're waiting for that, the next problem is very, very similar, which is that we just turn it into pure black and white. So what we do for that is we will, well, I'll get to that in a second. But again, all this code is that we figure out what the average value of all the colors is and divide by 3. That's how you create black and white. Sorry, or grayscale, which is what we think of when you say TV's in black and white. Yes. Because gray is when all 3 values of light are the same. Gray is when all 3 values of light are the same. So what we do is that we take the average amount of light in them and just make them equal. So we turn down so what this does is that we figure out the middle value, and by setting them all to the kind of being that middle average value, we are basically turning down the intensity of the light that's above that middle value and raising the intensity of the light that's below the middle value. That's all this stuff is doing. And because again, it's just gray. So now that we've got the grayscale value, we can turn it into a black and white image by setting a threshold value for your gray value, saying like, if the average of the colors is above this amount, then set them all to black by making them all 0. If they're otherwise, you can set it all to white. And this will give us an actual black and white image in here. So what we'll need is we'll need a gray value is equal to, and again, we would use the same thing we used in the last problem, which I will share. Okay. And then we'll have some kind of threshold. And I'll say like it's like let's say it's if it's above 128, which is half of 256. So if gray value is greater than 256, I'm not going to type the rest, or sorry, greater than the amount, greater than our threshold value, then we set everything to be white. Otherwise, so if it's got a certain, if the average intensity of light is above a certain threshold, set it to white. Otherwise, set it to black. And to set them to white and black, it's much easier. Right? So we can use, you just set everything to either being 0 or 255. So let me go ahead and hit the share code button. Okay. And then go ahead and take a couple minutes on this one, and then we'll move on to seeing how Sepia works, or Sepia, or however you pronounce it. The one that's really popular for that, rather than being the one that's rather than being grays, it's browns, which can be very ugly or very lovely, depending on how they're used. So this is fairly straight. This is, sorry. Your brain's dead? That happens. You especially if you're not getting enough sleep. I know there's a lot of days where I feel like I'm not getting enough sleep. It's all my fault. I will say, I do see how hard everybody is working in this class. And overall, I'm very happy about that. And I understand that, yes, a lot of you are struggling, but you're working very hard. And I do understand this is like the first like normal semester like in forever. And a lot of teachers are having trouble adjusting to that and giving the correct amount of workloads and dealing. And yet, even though it's the first normal semester in a while, we still have issues with illnesses and COVID still going on, even though it's not the forefront necessarily anymore. So I'm aware of that. Right. All right. So for this one, let's grab the gray value and calculate the same way as above, which is just take the average of everything. And then if the gray value is greater than amount or greater than equal to, honestly, it doesn't matter. If then it's above this certain intensity. So we're going to set it equal. So we're going to set the three values that we got here. The new, well, again, I'm a big fan of copying, pasting stuff that I've already worked on. We'll set them, we'll set all these values rather than being equal to gray value like we did last time. We're going to set them equal to 255, which is white. Else, set them to black. You're perfectly allowed to reverse the logic. Like if gray value is less than amount, then set it to black. Otherwise, make it white. You know, logic's like that. You can reverse the logic and it will still be valid. And then what we have to do is setting these values though and creating these variables isn't enough. We have to also create the new, pixel and tell the picture, hey, replace the pixel you have with the new pixel. So you could calculate it and wonder why it's not working, and it's because we do that. I'm going to change this to go faster. Oh, set delay 0 to turn off animation. Great. So if we run this now, okay, come on. There we go. And this is what an actual black and white would look like, where all the brighter pixels got turned to white and all the darker pixels got turned to black. If I reverse the logic here, if I get it the other way around, then it's going to become, and then the image is going to become inverted, which is also pretty cool. There's its own effect, right? Now, let's talk about one that actually gets used. It's the same as the one above. I will share it. Okay, so don't worry about trying to frantically scramble it down. Okay. All right, so this one, again, you'll want to take the logic, basically the base from number 1 to do from this first. For this one, again, I'd take the base ones from the first one to do this, where you've got the gray value, the new red, the new green, the new blue, right? I'd take that one for this one, which is sepia tones. So the sepia tone, again, it turns it, instead of turning it into grays, it turns it into browns. You've all seen it before. Kind of, you know, it's kind of this, different shades of brown. Sepia toning is a chemical process. Let's see, black and white. What examples? Geez. from the Latinized form of Sepia cuttlefish. Very interesting. Did not know that. But right here's a sepia image, right? It's notice that it's browns rather than blacks and whites or grays. Okay. Now to get the browns though, you don't want them to be equal. Instead, we use formulas. We have these formulas here where we don't take this, where basically we don't create a gray value. We just use a formula for each red, green, and blue. But fortunately, you don't have to figure out those values. To calculate the new red, if we want it to for a sepia, so for a sepia tone, we would have to set red, green, and blue, new red, green, and blue pixels. To figure out the new red, we take the red, multiply it by almost 40%, about 75% of the green, and then about 20% of the blue. And then again, the new green value has different values. So this again is just like a plug and chug kind of deal here, where where the new red is basically dependent on the old red values, right? So we figure out what the new red value is, the new green value is, new blue value is. We create a pixel like we did above with those values and set the pixel to that image. That's why I said like you might want to grab this over here, right, from the first code and drop it in here because it's the same thing. But we don't need this gray value anymore. And instead just fill out the new red, the new green, and the new blue based on the formulas, right? And the way we would get the red, green, and blue again is the p.get red, p.get pixel, p.get red, p.get blue, p.get green, and multiply them by the appropriate amounts. All right, so go ahead and try that. I know this is very outside the comfort zone for a lot of students, but I'm trying to push you outside of your comfort zones in like a, in a way that isn't that, high stakes. Get third parameter in the previous question. We don't get, there is no third parameter in this one, I think, but there is a set parameter over here in each of them, right? Image dot set pixel, and you're saying set this X and Y coordinate to be this new pixel. So here we get the pixel the original pixel, we create the new pixel, and then we say, hey, that pixel at X and Y, let's go ahead and replace it. All right, so for Sepia or however you pronounce it, let's go ahead and count. This is the red value. I can't just copy and paste it in here. I mean, you can. You just have to fix it, like you said. Right? So first off, all these X's have to go. Right? None of those are good for us. Can't do any of those, anything with X's. We need stars to do multiplication. I mean, they're not X's, they're multiplication symbols, but they're not part of your standard ANSI keyboard. Yes. Probably. I'm just trying to do it as this way to keep it formulaic. I didn't quite hear everything you said, but I think I heard, you know. Nah, it's also the distance. So okay, we've got these values, and then rather than red, we need p dot get red. And we just replace all the R's with p dot get red, all the greens with p dot get green. Okay. And then we've got p dot get blue. Boom, boom, boom. And hopefully this will work. I believe it said that 1 to 2000 will speed up the animation, which we definitely want to do. Where it's only drawing every 2000 pixels, I think, or something like that. And there we go. We've got this nice sepia tone of the golden bridge. There's a space here where you can try to where we can try to do these kind of things. Where we can let you experiment, like figure out how to do filters for neon, try it, you know, make multiple passes. But there's other code we can do. Go ahead and let's go. Actually, I'm going to skip the rotation because I want to move on to something a bit else, which is over here. So it says it's more advanced, but honestly, we're doing rotations a bit of a pain in my opinion. But what we needed, but here's an old picture. Let's take a look at this old picture. Right? So you've probably seen on the internet like examples of image restoration, right? Where basically you take an old picture and you make it look better or you upscale it, right? So let's take a look at a bit about how that happens. Okay, typically we use AIs to do it these days, but those AIs have some like specific machine learning process, but the basics are fairly straightforward. So here's an old picture that was gathering dust and got scanned, and you'll see that there it's kind of messy. It's got all these little flecks over here, right? Little flecks of, you know, looks like he's got pox on his face, you know, pox upon his house, and that he's got soot on his sweater, right? This is noisy. The picture in question here is noisyman.png. So how can we digitally restore this photo and make him look better? Well, what we're going to work, if we look at the pixel, all these places that are out of whack, all these soot marks or pox marks or whatever you want to call them, they're essentially just one pixel, okay? So we just have to fix each of those pixels. But how do we do that? Well, rather than just trying to go and figure out what that pixel is and try to do it individually, we're just going to cheat, essentially. What we'll do is that we will fix it based on what the pixels around it are. Okay, now I've never done this before, but I have a feeling I know how to do this because they tell you how to do it. So your first inclination would be to like figure, it says first thing you might want to do is look for all those bad pixels and just change those. But honestly, that's tough because how do I figure out what this is and how do I automatically detect that this is out of whack from the other pixels, you know? And the easiest way to do that is that there are two strategies. Every pixel becomes the average of the 8 pixels around it. Or rather than using the average, you can use the median, which is you figure out what the values are and, you know, choose the middle value. And it points out that it works pretty well because bad pixels tend to be around 0 to 255. They tend to be, you know, all the way black or all the way white, whereas the good pixels are more gray values. So to find neighbors, we will need to use some nested loops where we calculate the range of the loops based on the current pixel location. You don't necessarily need to use nested loops. I think I'll walk through this one rather than necessarily subject you to trying to do it yourself. So the process of iterating over neighbors of a pixel is called a kernel, and it's widely used in image processing. The one thing that they warn about, which is the thing that I had already looked up because I know it's going to be tricky, is that we have literal edge cases and corner cases, which is how do we figure out the average if we're on the corner, okay? Or on an edge. How do we figure out the average of 8 on the edge? We would like have to program that separately. So there's two things we do that, which is that we have we basically, there's the hard way or easy way. The hard way is to add conditionals, if statements to detect whether you're on the edge or not, and then change it up if you're doing them. The easy way is just skip everything that's on a border, which is what I'm going to do because I like easy. Okay. So here we're going to go. We're going to work on. So I'm going to go ahead and work on this. So how do I do this? Well, first thing I'm going to do is I'm going to load up the image in the same way that I did it before. Okay. So all of this so I'm going to copy paste all the nonsense that we had earlier. Next, I got to do that nested for loop. To do that nested for loop, I'm just going to grab, and I want to grab these for the drawing as well. Okay. And then honestly, it doesn't matter which dimension I do first, as long as I am doing it cleverly. So over here, I'm going to use X and Y instead of row and column because I can. For X in range, and then I will use image dot X goes across the width. So I'm going to do width here. All that matters is that my names line up, right? We were doing row column earlier, which had height, then width. But all that matters is that I know what I'm doing and that my names line up. So get width. And this will change in a bit. Y for Y in range, image dot get height. Now this will be changed very quickly because, as we mentioned, I don't want to have to deal with the edge cases. Right? Just making sure that this was exactly what I thought it was. Yeah, this is the range. Okay. So let's see. So first thing I'm going to do is I'm going to finish this off. Going to pass to make sure that this works. That I didn't mess up anything there. Well, it's the Golden Gate Bridge, so I messed up there. What I want is noisy man, all one word, .png, right? So the most common issue when you have files is that you're looking at the wrong file, the wrong path. Noisy man, .png. If you're trying to do it on your computer, it won't work. Like your actual computer, it won't work because you have to have this file on your computer. Okay. Now, this works. Let's go ahead and print out our XY combinations, right? Just for a second over here, right? And now the edge cases that I don't want to deal with are the ones that have x is equal to 0. Oof, that's a long one. I may have made a mistake there. X is equal to 0, or y is equal to, where basically the x is equal to 0 or the extreme value, or y is equal to 0 or the extreme value. Let's go ahead and stop this and reload the page, because I decided to run was silly and printed out too much. Okay. So instead, so I could do some if conditions, like if x is equal to 0 or y is equal to 0, or x is equal to image dot get width minus 1, y minus 1, because again the width would be 0 up to but not including get width. So right, again, if the picture was 5 pixels long, the pixels would be 0, 1, 2, 3, 4, and the get width would give us 5 because there are 5 pixels, 0, 1, 2, 3, 4. So get width minus 1. Or y dot get height. Sorry, not y dot get height, image dot get height. Oh, sorry, y is equal to image dot get height. I tried to do 2 things at once while talking. Right? Minus 1. In that case, I can just simply hit continue. And what does this do? It means that basically that I'll just skip this iteration of the loop and keep going. Okay, that's what continue does. It basically says, let's stop going. Or I could basically say pass and do an else statement, but I don't need to. This is just a way of me halting. The other way I could do this is that I could do some slicing over here to make sure that I don't do the beginning or end. Honestly, the slicing would have been less work, in my opinion, but not necessarily as easy to read the logic. But notice here, basically, I'm saying, hey, if we're on the left side of the picture, or the right side of the picture, or we're on the top of the picture or the bottom of the picture, just skip it. That's what we're saying. Now, why are we saying that again? Because I don't want to have to deal with those pictures and having edge cases for them. Okay, now I want to either take the median or the middle or the average value of all the values around me. So given a, right, annotate. So if I'm at this position, nope, if I am in this pixel over here at x, y, right? What are the 8 pixels that are my neighbors? It would be x minus 1. So remember, x, let's see, x minus 1, because again, left and right for x minus 1. And this is the one that's a bit confusing. Y minus 1. Y minus 1, because again, the y-axis over here is 0, 1, 2, 3, 4. It's this way. So you subtract to go up. It's really weird in computer science. Just one of those things. But it has to do with the fact that when we deal with grids and arrays, we start with, the row column kind of format. So this would be, this upper left square would be x minus 1, y minus 1, x minus 1, same y value, x minus 1, y plus 1. And we could basically do a nested, we can either list all 8 of these out individually, or we could just do it, or we could do a loop that would go over them. And what we would want to do is just simply add their values. So we would want, so let's see. So let's say we've got new red is equal to 0, new green is equal to 0, new blue is equal to 0, green. And each of these act as kind of a separate accumulator for the red, green, and blue value. So for instance, I could do this manually like so. I could say, hey, new red is equal to, sorry, new red plus equals, let's see what I want to do. Right, emit. Oh, right. So I need to get the pixel. I need to do image. Yep, image. So the current value is image dot get pixel is equal to, no, P is equal to image dot get pixel. I was just trying to remember it because again, first time I'm really working with this stuff. Equal to get pixel XY. So the new red would be equal to image dot get pixel. And let's start in the upper left, which would be X minus 1, my minus 1 dot. And you could totally change these dots together, get red. And then we would do the same for the green and the blue. And then we would copy paste this 8 times, and that kind of gets a bit ugly, you know? So, so instead what we can do is we can do a nested loop. A nested loop in our nested loop, I know. For X, so for X val in range 0, so we want -1 up to, but not including 2, go up by 1s. So for X value, for Y value, we could also do for it gets a pixel object, an object that represents, that is a code representation of a pixel. I mean, we can do set pixel, but what we're going to do is that, but I think it likes it better if we create a new pixel and override it. But I'm just following the form we've been doing, which is creating a new pixel and overriding it. So what we're doing here is that we're getting X value, we're getting the Y value, or the, yeah, and then we're going to do P dot, sorry, we're going to say other pixel is, or let's say neighbor, because that's what it is. It's our neighboring pixel. Neighbor is equal to image dot get pixel X plus X val Y plus Y val. Which will, and the amount that I'm adding here is either going to be -1, 0, or +1. It's one of those 3 values to each of those, and it's trying them in all possible combinations of that. Now let's see. For averaging, replace every pixel with the average of the 8 pixels around it. Okay, so we'll try that. The way we do that is that we are going to say, we are going to take these values over here, the new red, the new green, the new blue. We have the neighbor. And what we'll do is, rather than having manually going through and having 8 separate things to add, we'll do plus equals. Right, it's X val is a typo. Probably better named X offset. Plus equals 0, but neighbor dot get red Neighbor dot get red. Neighbor dot get green. Brett green, my bad. Get green. Neighbor dot get blue. And then there's one more clause I have to figure out, which is, of course, I don't want to add the pixel to itself for the consideration of its average, right? Every pixel is the average of the 8 other pixels around it. So what I'm going to do here is I'm just going to have a if x equals y. Can that work? If x equals y, and then do a not, would that work logically? Would x not, if x is not equal to y, equal to 0. So if they're both not equal to each other, so if they're both not equal to 0, I think it would work, but it'd be the first thing I'd check if it doesn't. Okay, so now that we've got these values, now that we've added everything up, we've added our eight neighbors in. What we're going to need to do is that we need to average these values. Now, how do we average them? Well, we just simply say, hey, the red value, we've added a bunch of stuff together. We added 8 pixels together, so we divide by 8. And we just do that for the rest of them. New green, divide by 8. New blue, divided by 8. Then we say new pixel is equal to image dot pixel to create a new pixel. And then we put in the new red, the new green, the new blue. Okay. Sorry. It's what I keep saying about typing and talking. Thank you. I totally missed that. New pixel. And then we do image dot set pixel. And then set pixel x comma y comma and then we would say new pixel, and then we invoke the prayer of all people trying something for the first time. Please work, please work, please work, please work. Again, this is fairly new to me as well. So error, image has no attribute pixel on line 28. So image dot pixel. So how do I make a new pixel? I just simply, oh, it's image, right? Image. We'd have to call the package itself to do that. Right? As opposed to img, which is the thing we have. So now it is currently running, I think. Oh, there we can see it go. It's making it a bit blurrier, but it's cleaning it up. It's a bit, the dots are still there, but they're harder to notice. Yes. Oh, here? Okay. Yeah, if x is equal to 0 or y is equal to 0 or x is equal to get image dot get width minus 1 or y is equal to image dot get height minus 1. Okay. Now the other way we can do this, as they said, is, so first off, this exceeded the time limit, so let's just simply up the, how fast it's going to go. Okay. And it worked. It's just a bit blurry now. So let's go ahead and try the other method. The other method is that it said was, hey, you've got these 8 values. Instead of averaging them together, let's figure out what the median value is. Okay. Yes. Yeah, so to get the median, so doing the median value is a bit different because rather than accumulating the values, we're going to do so rather than accumulating using addition to add numbers together, we're going to do doing addition to add numbers to a list. And then what we'll do is that we will sort the list and get the middle value from that list. Okay. So what do I mean by that? So instead, what I'll do is that I'm going to do the same thing I did over here, but I'm going to say reds is equal to a new list. Greens is equal to a new list. Because again, what does the median mean? It means getting the middle value. It's not as simple as adding things. Blues. Okay. Reds, greens, and blues. Same loop that applies. The only difference is that I'll actually include our thing this time. I'll actually include the one that we currently have. So for every pixel, including myself, what I'm going to do, let's see what I did. Replace every pixel with the median pixel value of the 8 around it. Okay. What I'll do here, I'll comment this out. We can always come back to it later. And what I'll do over here is I will, let's see. So what I have to do now is that we do the same thing. We say, hey, let's get the neighbor pixel. And rather than figuring out rather than like adding its individual values numerically, we're going to add them as though we're adding a list. So how do we do that? The way we do that is, one second, is that we would still do reds plus equals, sorry, reds is equal to reds, right? Rather than doing new red, a single new red, a single new green, what I'm doing is that I'm collecting all the values, not adding them together. Reds plus image, sorry, let's call it was the neighboring pixel dot get red. Except this is two different types. This is a list being added to a number. So there's two different ways we can add this to the list. The first is by doing this line, reds dot append neighbor dot get red, and that will this is how we accumulate into a list. The other way to accumulate into a list is to do a list addition, which is reds is equal to the list plus, and then we put this in a list. Because Python's nice and you're allowed to do it like that. It's up to your taste, to be honest, but I think that the way that leads itself to being more applicable to future programming and other languages is doing it this way, which is we say reds, hey, the reds list, add this red value to yourself. Same with the blues. And greens. So now we've got a bunch of reds, greens, and blues, but they're an unsorted mishmash of these values. And we want to get the median value, which means we want to get the middle value. So to do that, what we want to do is we want to sort these from least to greatest. Okay. And then we want to choose whatever's in the middle, which sounds like a lot of steps, but honestly, it's only one, because sorting itself is its own thing that we could devote an entire class to. But Python has its own sorting methods built in, Python sort, where it uses something called timsort, I believe, to do a lot of the sorting. There's two different methods. There's sort and sorted, and of course, because I've worked in multiple languages, I forget the difference between the two of them. Okay. Right. Sorted function returns a new list. Right. Okay. Yeah. Sorted, I believe, would give us a new list. Python docs sorted. Sorting how to. Sorted gives me a new list. And then list dots, if we take call list and tell it to dot sort, it will sort things in place. Okay. So let's see. So let's do this. Reds dot sort. Blues dot sort. Greens dot sort. And I was pretty sure that was the way it worked, but honestly, I always like to double check. It's good nature for programming because it prevents errors. You know, it's the whole measure twice, cut once. Okay, so now the new red should be the middle value in that list. Now, each of these has 9 values in it because we added the pixel in question into there. So, you know, it's itself. So there's 9 values, right? Index 0, comma 1, comma 2, comma 3, comma 4, comma 5, comma 6, comma 7, comma 8. Those are our 8 indexes. And the middle one would be index 4, right? And we've sorted this now. So the middle value from least to greatest would be an index 4. So the new red should be reds, comma 4. You could also do length red. I mean, the common way to do this is to do reds, length of reds, divide 2, figure out what that is. But honestly, why bother doing math when we know where it's going to be? The new green value is going to be greens blues 4, greens 4. So those are the values. And then we just use the code we already have to create a new pixel, set it, and let's see what that looks like. And let's see, again, we're choosing the median values here. And this is definitely looking like more of a AI ups. This looks more like, it's very, very smooth now, right? This picture got very smoothed out. Honestly, what this reminds me of is like some of the filters you can add to emulators for 8-bit games, where you do upscaling on that. So these kind of things are valuable. There's more, obviously, there's more advanced techniques you can use, but this is the basics of all the techniques, of all these techniques. Because the idea here is that, well, if we look at his forehead, each pixel is pretty similar to all the other pixels around him, right? And what we're doing here is that we're kind of blurring the edges. That's what we're doing. We're kind of blurring the edges where the big color differences come together, right? So what if I decided to put this back in where we don't consider our own picture in it, like our own current pixel in it. Instead, we choose, you know, now it's 8, we still choose 4, 0, 1, 2. So it's, I mean, 4 or 3 would be the middle in this case. We can use either. You still get kind of the same effect. So there's a lot of different ways to do image processing over here. As you can see, this is a big kind of exercise. Again, I'm going to share the code, but I want to give you a kind of taste of something different. And this is the kind of things you have access to now that you're working with files. Now, before I completely dismiss you, since it's, you know, so close, let's talk about what I'm going to be doing in the upcoming week. Okay. Let's just simply do a brief overview of what's going to be happening on Tuesday and Thursday. I hope to have the exams graded and entered, and then I will try my best to return them to you. I'm going to have to think about the most efficient way to return the group exams, you know, because there's got four people on them. But next week, what we're going to be doing is we are going to be doing module 8, where I'm expecting you to go over dictionary. I want you to review dictionaries, start learning about dictionaries. But what we're going to be doing is going over common words and Roman numerals. So we're going to be doing, so Thursday's exercise will go. So I want you to know about, so what I want you to know about how to do dictionaries by Thursday. Tuesday, we're going to do more, we're going to do another project. This one much more based on files and file processing. So much more relevant to the Python, to that Turtle homework. If you need adjustments on due date, please send me an email. Class is dismissed for today.
I've been working on lab 4 and 5.
Mm-hmm.
I have not been able to always get it down.